Hi, this is Amir Azadi, and I'm working in machine learning team at Wolfram Research. And today I will be talking about new unsupervised learning functions in version 12 of Wolfram language. Hello, everyone. Can you hear me? Everyone hear me all right? Yeah, good. So today I will be talking about some new functionality that we introduced in version 12. And we start with, so let's see. We first start with find anomalies and anomaly detection. And then we talk about synthesize missing values. So these are all purely supervised learning functions. And I will tell you how probabilistic modeling gives rise to developing these new functions to find and isolate anomalies and also to fill in missing parts of data. So first, I will start with anomaly detection and find anomalies. So what is the goal here? So given a list of examples, it can be numerical data, it can be nominal data, and we can ask, or it can be images, we can ask what are the data that are somehow different from the rest, from the majority of these. So I will explain in detail what do I mean by being different. And it can be very useful in many areas like fraud detections, monitoring the server for suspicious attacks, cleaning data, restructuring data. And in some literatures, it is also called outliers instead of find anomalies or anomaly detections. So we introduced 4 new functions related to find anomalies. It's anomaly detection, anomaly detector function, and find anomalies, and delete anomalies. First, I will start with few simple examples. First, find anomalies, you can just give it data with nothing, and it would return the anomalous examples. You can ask for different properties, like anomaly positions. By default, it returns the anomalous examples that it thinks that is different from the other ones. You can ask for properties like anomaly count. You can use it for different things, images, colors, and so on. The derivative function of this is delete anomalies that would delete the example that it thinks, that it believes it's anomalous. The other main function is anomaly detection, which returns anomaly detector functions. So you just give it the training data to train an anomaly detector function, and it will give you a small icon that have some description about the method that it uses that I will explain later, number of examples in the training, and then this new detector function, you can use it to find anomalies on new examples, and it returns a true and false, a Boolean list indicating which examples are anomalies, true, or non-anomalies, false. You can also use anomaly detector function as a first argument in find anomalies, and as a second argument, you can give it a list of new examples that you want to detect anomalies in. So just as a side note, current version of the function won't support finding anomalies, for example, in a given example. If you have one image and you want to find some anomaly in one image, or you have a time series and you want to find anomaly, a rare event there, this does not work. It is an anomaly example among other examples. So we hope that you would have that feature in the next part. So, but let's think about what is an anomalous example. So if we go and look at naively Wikipedia, we come up with this simple definition that rare items which raise suspicious by differing significantly from the majority of the data. So examples being different somehow. But what does that mean? First, let me tell you that if anomalies are not too diverse and you have a lot of anomalies, you can have a supervised learning approach. And if you have labels for some data with labels that are anomalies or not, and you can use classify for that. But here, for FindAnomalies and related functions, we're focusing on a problem where you don't have that many anomalies. They're rare, and you cannot get that much information about them. So anomalies would be things that are, you have a lot of, a big space and you have little data. So supervised learning approach will fail to identify those. And we can formalize here this problem using probabilistic approach by learning, by modeling non-anomalous data and figure out how extreme an example is. So this is a purely unsupervised approach to anomaly detection. So, but how this our formalism work? So let's assume that the data is generated based on some distribution. There's an underlying distribution that of non-anomalous data that we somehow know what that is. So by distribution, I mean a statistical distribution. So an anomalies here would be the examples that are out of distribution. So this is a very essence of a density-based methods here. So we are strictly speaking about out of distribution example by saying it is the probability to generate samples with a lower PDF than the given example for a specific distribution. So it means that the total probability of all examples whose PDF is smaller than the given example. So it means that we're trying to measure how rare one event is, one example is. So you can see that, yes, all the total probability of any events with PDF lower than a given example X. So for example, if for a given distribution, a normal distribution with mean 0 and a standard deviation of 1, we can ask for rarer probability of generating 4. So it will be very rare, very extreme event to have number 4. So we can think of this rare probability as a generalization of a p-value for non-normal distributions. And we introduced rare probability in version 12, and you can use it like first argument would be the distribution, and the second argument it would be the example that you would want to know how extreme that example is given the distribution. So examples are considered anomalous if their corresponding rarer probability is below a given acceptance threshold. Just to be clear, rarer probability is not the anomaly probability. It is just a measure of how extreme one event is. So we can ask for the rarer probability using anomaly detector function, training a detector function with anomaly detection. For example, on a set of random real numbers between 0 and 1 and two-dimensional vectors, and you can call with the property rarer probability. And for example, you see that this first example, since the X component is 5, it would give you a very small rarer probability. So this would be considered anomalous. But you can change this acceptance threshold for the rarer probability below which one example would be considered anomalous also by hand. The default, if you don't specify it, it's 1 in 1,000. But let's take a look at this acceptance threshold. So we create a random 3D vector of anomalies, just few of them with negative values, and the majority of data is random real numbers between 0 and 1. So you can see the anomalies here, and the majority of data are normal data here. So if we can just use FindAnomalies on this set of data, and it will give us identify correctly these anomalies with automatic acceptance threshold. But say you want to put an acceptance threshold 0.2, which is pretty large. It's like 20%. And you will start to see that it will pick up points at the edge of the cluster of the nominal data also as anomalies. So these are the points sitting at the tail of the distributions. So in general, if data comes from the same distribution as you have for the data for the training your detector, this acceptance threshold would correspond to false positive rate, that like these points that are normal, but it would find it as anomalies. So, but first, we need to find a distribution on anomalies-free data, data without any anomalies. So this is a dilemma here, because on one hand, first, the ideal case is you have a training data with no anomalies, so you can train it, and then you can use the anomaly detector function on new examples. But what if in your training data you would also have anomalies? So this is like you need a distribution without anomalies, but you need to, the point is you want to find anomalies first. So this is like a chicken and egg problem. So there are a few methods to resolve this problem. One method is cross-validation type method, that you split the data to training and testing, and you train on some examples, and you test the distribution on other examples, and you pick the examples with a small probability as anomalous, and then you do it vice versa. After removing all the anomalies by cross-validation, you retrain a distribution on the anomaly-free data. And this method would work if you would have no duplicates in anomalies. But if you have like anomalies that are similar to each other in one point, you might put too much mass distribution on top of that, and you would make the probability density large on those points, and you would just make mistakes. There are other approaches like clustering type approach, that you start with a small seed of data that you're confident that is normal. You train a distribution on that, and you keep adding more and more data, and you grow your normal seed. And you would stop until you hit some threshold. And whatever is not in the bag of your normal points would be considered anomalies. So this method also can easily fail if you have a group of points that are like further apart. So this normal growing process might stop early, and you would leave with a lot of normal data that you think that are anomalies, but they're not. We implemented the first method, and we will add the second method and more methods in the future. Let's look at properties of some practicality of using these functions. So you can use FindAnomalies with different properties. You can ask for anomalies, which is the default, and it will return the examples that things are anomalous. You can ask for anomaly positions, where in the list those examples exist, non-anomalies, the normal points, and a list that is anomaly Boolean list, which is a true-false Boolean list indicating whether the examples are true or not, are anomalies or not, and rarer probability for each of them. So let's look at one application of anomalies for images. So here I get a training and test set of MNIST data, images of handwritten digits, and I also make a test set with a few anomalies, a picture of a monkey and an image of a blurred, noisy digit, and I just add it to my test set. So this is like the cleanest way that you can use anomaly detection. That you train, I just train on the digits that I know that it's without any anomaly, and then you can specify the methods. So the methods are the same as learn distribution methods. So I just pick multi-normal. You can also use a performance goal. So at the core of anomaly detection function, it sits the learn distribution, and the methods are the same for learning the distribution. And then you can learn the anomaly detector function on your images, and you can use FindAnomalies on the test sets with the anomaly detector function that you trained. And you would see that it would pick out of these digits and anomaly cases the ones that are not anomalies. So, like many times it might, especially for images, because the space is large and probability densities are a little bit hard to define in larger spaces, in multidimensional, high-dimensional spaces, you might need to manually work with acceptance threshold to make it smaller than what we have right now. We resize all the images and conform it to the same size. So if you have different size images, no, it won't find it as anomalies. Yeah. And you can also look at, after training your anomaly detector function, you can look at the information, and you can get the summary of the training process that you had. Like you can get the data type, its image, like what's the dimension, what's the method, what's the loss function, and so on. So so this was all about anomaly detection and FindAnomalies. So briefly, I would also talk about another unsupervised learning function that we developed, which is synthesize missing values. The goal of it is filling missing values in each example by a generated value. So by default, if you have a data set with symbols missing and indeterminate, it would pick them up as missing values, and it would just fill new values for that. So the formalism is that we train a distribution on non-missing data, and then we condition that distribution on known variables. For example, here we have like the first variable, the x variable, to be missing. So we condition on y, the second variable, and we find this conditioned distribution, and we draw a sample from it, from this conditioned distribution. So there are two ways that we can draw a sample. We can just draw a random sample, or we can get the most likely sample, and which correspond to an example with the largest probability. So you can just use synthesize missing value directly on your data with missing values, or you can have a learn distribution and learn the distribution in advance on your training data and use synthesize missing value first argument with the learn distribution and second argument with the missing part. So, but let's take a closer look how it works. So imagine I have a two modal distribution, two multi-normal distribution with different mean and with different covariance, and you see the regions of high probability closer to the crowded regions and so on. I just generate a list like 20 candidates for one data point with a missing value on y-axis. So, and I just like plot it here, and you see that it follows these candidates of missing values, follows the distribution, strictly speaking, that draws from the same distribution, conditioning on one of the unknown variables. But you can also ask in the method to find the most likely example with mode finding. And you would see that by these purple points, that it would go and sample from the part of the region of the probability distribution with the highest, with the largest probability. So these are the most likely cases. So in general, you can set your method to have different learning methods for learning the distribution, and evaluation strategy for could be random sample or mode finding. So I told you that by default, synthesized missing value would pick missing and indeterminate as missing, but you can change that. There's an option missing value pattern. You can tell that like 4 is missing. Just fill in wherever you see 4. Or you can have a function. Wherever you see anything smaller than 3, just treat that as missing. This would be useful, for example, for if you have corrupted images. Here again, I have MNIST data, and I train a distribution on these on these images, and I just made some corrupted images, and I say that it should consider the pixel value 0.5, strictly the color gray, as missing, and it would fill in that with the draw samples for those, and would fill in the thing that it just imagine it kind of the model. I let the model to imagine what should be in those areas. So in the future, we would have a pre-trained synthesizer that you don't need to train it, especially for things like images that it might take time. And we would have the representation of missing values for different type of data, and so on. So I will finish here, and I would be happy to take any question.